Hi, welcome to your lesson on the t-test in statistics. And since we have Mr. T here from the A team, and I hope you know who that is, I'm going to throw in a little appelé de fou who doesn't study the t-test. So let's get started. Let's study. All right, the t-test tells you how significant the differences between two groups is. And a natural question might be, well, doesn't the chi-squared test tell us the same thing? Because in the chi-squared test, we had, for example, tables of data like this, where we were comparing one variable to another. And in this case, we have gender here, and on here we have chocolate preference. And we were trying to figure out, okay, does gender influence chocolate preference, or does chocolate preference depend on gender? So isn't that already comparing two groups? A gender group and a chocolate group and seeing if there's an influence there. So that's a common question. When do I use t-test? When do I use chi-squared test? So we're going to take a look at that first before we begin t-test. When should we use one instead of the other? Let's take a look. Okay, so chi-squared test. Normally in a chi-squared test, we set up a null hypothesis that looks like this. Two variables are independent of one another. Right? In the chi-squared test, we're typically looking for independence or dependence. So the null, or the status quo, is these two things are independent, they do not affect each other. In the t-test, a null hypothesis is going to look like this usually. The means of two data sets are equal to one another. So in this case, we are comparing two data sets like we are here, but we're looking specifically at the means. So we're saying if the means are basically the same, then we're going to say the two data sets are basically the same. But if the means are very different, then the two data sets are different. And it's similar to this, but you'll see the differences in a moment. So in the chi-squared test, it requires categorical variables, and that means we have categories on each axis, and we saw that with the the chocolate, milk, dark chocolate, and so on, and the gender. Those are categories were there. And it says usually only two categories, but each may have a number of levels. In the t-test, it requires two variables. One must be categorical, so one of the variables is in categories, and has exactly two levels, and the other must be quantitative and estimable estimable by a mean. So let me show you what that means in terms of data. So here's a data table, and again, it looks like a typical chi-squared data table. We have regions of the world here, and we have Europe and China, and then Europe is broken up into Northern and Southern Europe, and China is also broken up into Northern and Southern. And we're comparing the heights of people. And here we counted, in our sample, we counted 15 people with a height less than 150, and then people greater than 180, so it would be like tall people. There's 13 counted there, and you can compare the data. So this is a typical data table for chi-squared, where we have two categorical variables. We can see these are categories, and here the second variable, also categories of height, like maybe shorter, medium, tall. And then we have any number of levels here. Okay, in the t-test, if we looked at the same data, let's say, and we're looking at European heights versus Chinese heights, for t-test, we need to have only one category here, but only two levels. It says exactly two levels. So we took those four and we collapsed them into two levels. So just Europe versus China, and then the other must be quantitative. So rather than having counts of people by category, when we're doing a t-test, we just have all the raw data. So I just put all the heights in there. So that's important for a t-test. It's just the raw data. But we can, let's say we began with this raw data. It's typical that you go from t-tests to chi-squared by then grouping this raw data into categories, and then you can run a chi-squared. But t-test, we need the raw data like this because it needs to be a data that you can find a mean for. And more specifically, it needs to be data that is normally distributed. So we haven't mentioned that yet, but this data must be normally distributed. And heights typically are normally distributed. Okay, so let's go on. Let's just emphasize that point one more time. The data for a t-test must be normally distributed. So if you have raw data that doesn't follow a normal distribution, you cannot run a t-test. Okay, so here's the situation we have. Maisie noticed that the sun shines more on one side of her garden than on the other. She wanted to know whether this had any effect on the heights of the tulips on either side of the garden. So let's say she measured things and she got this data here. So on the shady side of her garden, here were the heights of tulips, and on the sunny side of her garden, here were the heights of tulips. And notice I've already color coded these. I kind of made groupings of like short, medium, large. So short tulips are from 21 to 25, And you can see on the sunny side, there's fewer short tulips. And then medium tulips are from 26 centimeters to 30 centimeters in height. And we can see we have about the same amount on each side. And then tall tulips are from 31 and above. And you can see there's more tall tulips on the sunny side. So just looking at the color coding, we can kind of see that in general on the sunny side, the tulips do look like they're taller. There's less short ones and there's more tall ones. So now our goal is to say, well, we have two sets of data. Can we say that the mean is significantly different? In other words, is the mean of this data significantly different than that? And then we can say, well, if it is significantly different, then that means the sunny side does actually produce taller tulips. So let's take a look further with that. So let's talk about the p-value, because a t-test, just like a chi-squared test, will produce a p-value. And the p-value refers to how likely something is to have happened by random chance. So we've been talking about that already, but I don't think I've used the wording of random chance, but that's basically what it means. If you have a p-value of 5.05, which is 5%, that means there is only a 5% chance that those observed outcomes could occur randomly, right? And that's what we've been talking about. The smaller that p-value, the smaller chance that our observed values would have occurred randomly. Okay, so here's what the t-test produces for this one, and I'll show you how to run this on your calculator in a moment. But for this one, our t-test, when we ran a t-test on these two sets of data, produced 0.199. So that means about 20%. So what that means is there's about a 20% chance that randomly this data will be different from this data in the way that was. In other words, that this mean was different from this mean in the way that was. So 20% chance, that's a pretty big chance. There's a 1 in 5 chance that tulips would grow in with this kind of variance. Like some would be in these heights, some would be these heights. So in that case, you're saying if there's a 1 in 5 chance of that just happening randomly, then maybe the sun does not have an effect, because it's pretty likely that that would happen just randomly. Okay, so that's how we interpret the p-value. So if we had the null hypothesis that the means are equal, remember for t-tests we usually set a null hypothesis like this, then we would accept that null hypothesis. We would say, yeah, I accept that. There's a pretty big chance this would happen randomly, therefore I accept that the means are basically the same. There's no difference between this data on the sunny or shady side. And then we would reject this if we had this p-value lower. Like for example, we usually set a significance level of 5%, and that's what's typically done in a t-test. We could say we want this number to be below 5%, and then we can say, okay, that is pretty unlikely when it's below 5%. If it's 5% or less likely that would happen randomly, we can say, okay, that shows that there must be a significant difference here. Okay, let's take a look at this one now from the perspective of a chi-squared test. So now I took this raw data and I categorized it, because remember with chi-squared we need categories. We already had the shady sunny categories here, but the height was just height data. So I took the height data and grouped it, and that matches the colors I have here. So I have 7 short plants in the shady one, but only 5 short ones here, and so on. And then the blue ones are here, 10, 10, and then the tall plants are here. So sunny side has 8 tall ones here. So I categorized both axes, and now I can run a chi-squared. And the chi-squared statistic there is 0.619, and the p-value there is 0.734. So again, these are different p-values because these are different tests. But this p-value here in our chi-squared test, again, tells us that to get the differences between this observed data and what would be expected, well, there's a 73% chance that that could happen randomly. That whatever difference we observe between this data and the actual expected data is 73% likely that that chance could happen randomly. So that tells you, wow, basically it's very likely that that could happen randomly. So it confirms what we saw here, which is we can say we don't accept that there's any difference between shaded and sunny. So in this case, our null hypothesis would have been height is independent of location. And again, we accept that. Just like we accepted that the means are the same, which means the data is basically the same, here we accept that they're independent. The shadiness, sunniness does not have an effect on the height of the tulip. So I hope that example kind of brings the two tests together and you can see how they work. Now let's do two particular tests for t-tests. But first, so the best way to compare two data sets is to use a t-test. A little bit of history. William Gossett, who was employed by Guinness, that is the beer maker in case you don't know. He was employed to improve the taste and quality of their beer. In order to monitor the quality, of the hops that were used in the brewing process, he invented the t-test. So he did it just for the purpose of making better beer. He published under the pen name Student. Hence, it is sometimes referred to as Student's t-test, which is kind of funny. There's a plaque here in the Guinness headquarters that recognizes his work. And here is what he looked like, and his full name was William Seeley Gossett. And a little bit more of the history, he published his work on the t-test in this publication, Biometrica, in 1908, but he was forced to use the pen name, which is Student, because his employer regarded the fact that they were using statistics as a trade secret. So they didn't want other brewers to know that they were using mathematics to make their beer better, so they said, hide your name, and he just used the name Student when he published. Interesting history. All right, so when we're doing the t-test and hypothesis testing, the null hypothesis is usually the means are equal, and that's what we looked at. For the t-test, that will be our null hypothesis. One mean is equal to the other mean for the other set of data. And the alternate hypothesis, H sub 1, would then be that the means are not equal, or sometimes we have what's called a one-tailed test, that one mean is greater than the other or one mean is less than the other. So either you're just saying, hey, the means are not the same, or specifically, I think one mean is greater or less than the other. And the p-value we know measures the probability of that happening by random chance. And in t-test, we're typically going to use a 5% significance, but we can also use 1 and 10% significance like we did in chi-squared. Okay, our first example here. Mr. Arthur gives his two chemistry groups the same test. He wants to find out whether there's any difference between the achievement levels. So here's group 1's achievement, here's group 2 achievement. We have two sets of data. Both of them can be normally distributed because grades are typically considered normally distributed in a bell curve. So we can compare that using a t-test. Write down the null and alternative hypotheses, and then let's run the t-test. So we're going to use the two-tailed test hypothesis, alternate hypothesis that the means are not equal. So let's see, what do I have here? Okay, so null hypothesis, the means are the same. That means the data is not significantly different from one class to the other. And then alternate hypothesis, the means are not the same. And then we get a t-value of 0.235, sorry, a t-value of that and a p-value of this. So let me show you how to run that on your calculator. So if you have your calculator, you're going to press on here. And just like we did with goodness of fit test, you're going to go to stat. We're not going to use a matrix for this. We have raw data, so we're going to use stat and then number 1 edit, and then you're going to enter your data into two lists. So I've already entered it. Take a moment now to pause and enter your data. So here's list 1 and list 2. I have all the data here. Okay, now that you're back, let's take a look. Now you're going to hit stat again, and you're going to go to tests, where we've been going recently, and you're going to look for the t-test, but you have to go down to this one number here, number 4, 2 sample t-test. We have 2 samples, t-test. Enter. Here we're going to always use data. We're going to use the data we've inserted, and the data comes from list 1 and list 2. Keep all those the same. Here is where you set your alternate hypothesis, right? You can say the first mean is not equal to the second mean, or you can do the thing where it's less than or greater than. But in this one, we're looking to show that the two means are not equal. So I'm going to select that one, enter. Where it says pooled, we do yes, because I'll explain what that means in a moment. And at the bottom, we're going to do calculate. So enter. And it gives us the t-value, which matches the one we see here, and a p-value also, which matches this one. Now, our p-value is very high. That means there's an 82% chance almost that the difference between these scores would occur just randomly. So in other words, we accept the null hypothesis that the two means are basically the same, because it is so likely that any differences that occurred here would happen. There's 82% chance that these differences would occur randomly. Therefore, we say, okay, then there's no difference. The two data sets are basically the same. They have the same mean. Okay, in case you're wondering, so that's the p-value, but in case you're wondering, well, what is this t-value? Because this is called the t-test, so what is t-value? Well, t-value just measures the size of the difference relative to the variation of your sample. So here, you do the difference of the two means, and on the bottom, you do a calculation to show the difference in the variation. You're not required to know this formula, but I know some of you are probably thinking, what does this t-value mean? So that's that, and you can research some more yourself. Okay, the second question is this. Pause and read it now. And we're trying to figure out if there's a significant difference between the original fuel and the new fuel. So you're going to run the t-test on your calculator, and now let's check your work. We're going to run a one-tailed t-test this time because we're looking to see one is better than the other. and we get these results, and we can make this conclusion. Please check, pause and check this carefully.